Hi friends, in this video I will discuss the fundamental theorem on gradients, divergence and curl. These are basic theorems in the vector analysis and they are important in electrodynamics. So it is the basic or fundamental theorem of calculus that if fx is a function of one variable, then the fundamental theorem of calculus says that a to b f dash x dx equal to fb minus fa, where f dash x means it is the differentiation df by dx. So this was the fundamental theorem of calculus, and using this calculus, if this f dash x is replaced by the gradient, then it becomes the fundamental theorem of gradients. And the statement is the line integral of a derivative means here it is del t, gradient, is given by the value of the function at the boundaries. At the boundaries means at the endpoints b and a, and if function was t, so it will tb minus ta. So this is the fundamental theorem of gradients. And from point a to b, if a small displacement vector is dl, so it can be added up from dl1, dl2, dl3, and if the for different elements we find del t dot dl1, del t dot dl2, and finally we will get this t, it is finally tb minus ta. So this is the fundamental theorem of gradients, that it depends only on the endpoints del t dot dl and from path a to b. And this is line integral. So line integral is independent of the path between the endpoints, and it depends only the endpoints. And for a closed path, if this closed path, for a closed path, the line integral is 0, because if point b comes to point a, then ta minus ta, it will be 0. So line integral is 0 for the closed path. So now we will discuss a question example. We have to check the fundamental theorem of gradient for the function t, which is function of xyz, x square plus 4xy plus 2yz cube, and the path is given that it varies from 0 0 0, this origin, to towards x-axis 1 0 0, then towards this point 1 1 0, and then finally it go to point b 1 1 1. So we have to find out this along this path whether this function is satisfied the gradient theorem or not. So first we have to we know the fundamental theorem of gradient is a to b del t, that is gradient dot dl, it is equal to tb minus ta, the value of that function at point b minus at point a. So tb minus ta, if we can find out the value of this function t at endpoints, means 1 1 1 1 and 1 and 0 0 0, these are the endpoint. B is the endpoint, a is the starting point. So it will be, if we put the value 1 plus 4 plus 2, 1 we put 1 1 1, x equal to 1, y equal to 1, and z equal to 1, then 7 minus, when we put x y z 0 0 0, it will 0. The right hand side is 7. And for the left hand side we have to find out first the del t and dot dl, but dl vector is for these three different paths. So we can write a to b del t gradient t dot dl equal to, it is del t dot dl for path first. Path first is when we are going in this direction, then plus path second, this value left hand side, plus third for the third path. We have to add these values, and del t, first we have to find the gradient of t. So t was the function given as x square plus 4xy plus 2yz cube. So if we the gradient is the, when we operate this scalar function with the operator del. Del means I delta y delta x of t plus j delta y of t plus k cap delta y delta z of t. And if you differentiate, then we will find 2x plus 4y I cap plus 4x plus 2z cube j cap plus 6y z square k cap. So del t is fixed for the this left hand side. So for path 1, del t dot dl. So path 1 means when dl vector means only it is increasing in x direction. dx I cap and dy and dz is there is no change, so dl vector is only dx I cap, and for that y equal to 0 and z equal to 0, we can put y equal to 0 and z equal to 0. Del t means if you, this was the function del t, and if you put y equal to 0 and z equal to 0 in this function, then we will have 2x plus 4y, and with x cap only, because other things will give us 0. Then I cap dot I cap 1, 2x plus 4y dx, and the limit from x varies from 0 to 1. So x is going from 0 to 1, and we can find out this y equal to 0, so put y equal to 0, and then 2x equal to integration 0 to 1 2x dx, so x square by 2, and finally we have 1. The value of path 1 is 1. Part 2, in part 2 only dl vector is changing in dy direction, so dl will be dy j cap. In that case dl vector will be dy j cap, and x is varying, x is equal to 1 constant for this, and z equal to 0, that is constant. Only variation is y, so we will put the limit for y 0 to 1 dy, and del dot t was 4x plus 2z cube for this j cap direction. So j cap will give this value, other things will give 0. So now if we put z equal to 0 here, so we have 4 and x equal to 1, so it is 4 dy, and that is 4. Similarly for path third, the change is only in z direction, it is variation is in dz direction, so dl vector will be dz into k cap vector, so only this will, the 6yz square will be give us the del t dot dl, and for the limit on z equal to 0 to 1, it gives us 6, and integral of z square equal to z cube by 3, and it will be 2. So if we add these three paths, 1 plus 4 plus 2, that is 7, and also right hand side was tb minus ta, that was 7, so that's why gradient theorem is verified this for this function t. Now we move to the fundamental theorem for divergence, and it is also known as the divergence theorem, sometimes Gauss theorem also, or Green's theorem, and it says that the integral of a derivative, so here derivative means del dot a, it is the divergence, because in fundamental theorem of calculus it was f dash, so here it is del dot a, the derivative of or the divergence over a region, means it volume integral is there d tau, so volume integral of del dot a d tau equal to the value of the function at the boundary. So in the case surface is the boundary for a volume, so it is the surface integral or the total flux a dot dA. So it changes to the volume integral into surface integral, and we can see that if we have a small volume dV, and a vector function a or vector field is coming out of this, so it will be divergence of this function, so total divergence coming out of this small volume, so the liquid vector field how much diverges inside a volume. If we have a volume dV or d tau, so how much this divergence in this volume dV will give, or d tau, this should be equivalent to the flux passing through the surface. So surface is this outer boundary of this volume, so total lines coming out of this volume is equal to the total lines, vector lines going out of the surface. So this is equal, because whatever vector lines are coming from this volume, inside this volume, that is equal to the lines going out of this surface. So this is the fundamental theorem of divergence, and it also relates the volume integral to surface integral. So for a volume, the boundary is the surface, closed surface. Now we have an example. We have to check the divergence theorem using for the function b is a function, vector function y square x cap plus 2xy z plus z square y cap plus 2yz z cap for a unit cube situated at the origin. In this figure we can see it, we have a Unit cube means all the dimensions are of unit 1. So a cube has 6 faces and the volume of cube is written as dx dy dz, or d tau equal to dx dy dz. So first we need to prove the divergence theorem. So divergence theorem is del dot b d tau equal to surface integral of b dot dA. So first, if we find the left hand side of this integral, that del dot b d tau. So for that we need del dot b. So b is this vector function. So del dot b means the divergence of this. We have to the dot product of del with the vector, given vector. So it is in Cartesian coordinate system because x, y, z are there. So we can take the del y delta x cap plus delta y cap plus delta y delta z of z cap dot v. B is the vector y square x cap plus 2xyz plus z square y cap plus 2yz z cap. So dot product will x cap will give us the value. So delta y delta x of y square, and similarly delta y delta of this 2xy plus z square and delta y delta z of 2yz. Other terms would be 0. So now we have to differentiate it. Delta y delta x y square. So we are doing the partial differentiation with respect to x, so it will be 0. Here we are doing with respect to y, so only y term will be differentiated, others will be treated as 0. So it will give 2x plus 0 plus delta y delta z of 2yz. So 2y will be out and only z it is 1, so 2y. So we have the 2x plus 2y. This is del dot v. The gradient of this function is 2x plus y, and now we have to put this in left hand side. Del dot v d tau will be 2 times x plus y. This is the del dot v, and d tau is dx dy dz. D tau, that is the volume element, and if the values for x, y, z volume integral, we have the triple integral, and x is going from 0 to 1, y is also going from 0 to 1, and z is also going from 0 to 1. So we will have 2x dx dy dz and plus 2y dx dy dz, and if we integrate it, then we will have 1 into 1 into 1 plus 1 into 1 into 1, that is 2, because first you have to integrate dz. This will give us 1, dy is 1, and x dx will give us x square by 2. So it and 2 will be cancelled. So 1 it will also give 1. So 1 into 1 into 1. Similarly here 2 y square by 2 and other things will 1 and 2 cancelled out, again it will be 1. So left hand side is the volume integral del dot v d tau is equal to 2. So if this theorem is should be satisfied, then the right hand side should also come 2. But right hand side is the surface integral of this for the cube. We have 6 surfaces, so we have to calculate this surface integral will be addition of the total flux from all the 6 surfaces. So if we take this around plus x direction phase 1, second phase is in minus x direction, third phase in plus y direction, fourth phase in minus y direction, fifth phase we take in plus z direction, and sixth phase in minus z direction. So now we will have to find out the right hand side, that is the surface integral we have to find out. So b dot dA for the closed surface will be for first surface b dot a plus second plus third fourth plus up to 6 surface, means all the faces, 6 faces. So and b equal to y square x cap plus 2xyz plus z square, it is given value of that function b. And for the first part or first surface integral is b dot dA. So b is given. So how we take the dA? It is important because dA means the area vector. So area vector for the x cap direction. For the x cap direction, the area vector will be dy dz. So b dot dy dz, and if we only x cap will give us the result. So other things, x cap dot y cap will 0, x cap dot z cap will be 0. So only x cap dot x cap will give us 1. So we will have only b dot dA equal to y square dy dz in this case, and the limits are always 0 to 1 because for x, y and z all limits it is a unit cube, so 0 to 1. So y square dy dz means 1 by 3, y cube by 3 will be integral, and dz will give us 1. So 1 by 3 into 1, that is 1 by 3. Similarly for the second phase means first phase is in plus x direction, second phase in minus x direction. So the area element in that case will be minus dy dz in x cap direction. So it will be minus 1 by 3. Same values will be there, but only minus is there. Third phase is in y plus direction, that is this one. Third phase is in plus y direction. Fourth phase is in minus y direction, and for the y cap direction the vector will be dx dz, and here minus dx dz. Similarly for the z plus direction, the surface will be made from dx dy plane. So we have to again do for the third integral, that is y cap direction. So only y cap will, this value 2xy plus yz square, this will give us the dx dz direction, and dx dz plane, and 2xy plus z square dx dz. And if you have the surface integral of this, then 0 to 1 on limit z dz, and 0 to 1 for the limit dx. So we can write it separately, 2x dx dz integral, surface integral, plus z square dx dz 0 to 1. So for the 2x dx dz, we can have dz integral is z, and 0 to 1 means 1, and 2x means x square by 2, so it will also give us 1. So 1 plus 1 by 3, that is 4 by 3. Similarly fourth is vector is in minus y direction. So in this case minus dx dz b, it will give us value minus 1 by 3. Similarly for the top phase positive z direction, z cap, dx dy will be the area vector, and in z cap direction. So b dot dx dz z cap. So only z cap, this will give us 2yz will be 1, other things will give us 0. So 2yz dx dz, and if we put the surface integral, the limits, it is 1. Similarly for the sixth phase, b dot dA, sixth phase means the bottom going down. So z cap minus dx dy, and it will give us 0 to 1, 0 to 1 on x. Dx limit is 0 to 1, and for z also 0 to 1, so it will give us 0 values. So total is 1 by 3 minus 1 by 3. If we add these all 6 values, it will again, it is giving 2. So left hand side was 2 and right hand side is also 2. So now we have we can say that this divergence theorem is verified, or the Gauss divergence theorem is verified for the given function for this Q. Now the last theorem is the fundamental theorem on curls, or it is also known as the Stoke's theorem, and it relates the surface integral to the line integral. So for a vector function, the integral of the derivative, so integral of derivative means here it is a del cross B, it is the curl of V over a surface dot dA equal to the value of the function at the boundaries, and boundary means here it is the perimeter, the outer boundary of that surface is perimeter. So we can mathematically we can say that curl of V dot dA equal to line integral of V dot dl, and physically we can say that if we have the curl of a vector, if we take very small areas, and if we have one small area here, one small area here, one small area here, so these common directions will cancel. This is going up, this is going down, so it will be added up. Similarly this is added up, and all the inside walls will be added at, and finally they will move towards the outer boundary. So if something is inside, so after some time curl means it will go at the boundary, and this is the line integral. Boundary is the line integral. So right hand side is this, and left hand side how the curl vector small. If we take very small curl, and then small we add up these small curl up to full surface, it will give us this whole thing will go to at the boundaries. Here also this is the left hand side del cross B dA, the curl goes towards the boundaries, and finally it is the line integral at the boundaries for the closed surface. So this is the Stokes theorem. The integral of the derivative over a means the integral of the curl over a surface is equal to the value of the function at the boundaries, here the line integral v dot dl. And let's do one example for the Stokes theorem. So if we have a vector function 2xz plus 3y square y cap plus 4yz square z cap, check Stokes theorem for the square surface shown in this figure. Square surface is on yz plane, it is in yz plane, and the line integral we can say that it is from 0 to 1, then this is first part, second part, third part and fourth part. So the Stokes theorem is del cross b dot dA for this vector should be equivalent to the line integral for the total path. So total path is first, second, third, fourth. We have to add these all line integral. Right hand side, left hand side is the curl on dot dA. First we have to find the curl of this function, vector function b. So it is in x, y, z. So it is in Cartesian coordinate system. So del cross b will be x cap, y cap, z cap, delta y, delta x, delta y, delta y, delta y, delta z of the component of this, because on there is no x cap, so it is 0, 2xz plus 3y square and 4yz square. And if you expand this using determinant method, it is 4z square minus 2x, x cap plus 2z, z cap. And the area vector is in yz plane. So yz plane, this area is in yz plane. So we take the area vector dy dz, and the direction will be perpendicular, x cap direction. So area vector is dy dz. So now we have to take the the left hand side del cross b dot dA. So 4z square minus 2x, x cap, and x cap dot x cap will give us the value. This will give 0. So only we have 4z square minus 2x dy dz, and the limits are 0 to 1, 0 to 1, because on y is also varying from 0 to 1 and z is varying from 0 to 1 for this area. And finally we get, if we integrate this function, because x is equal to 0, x is not varying in for this area, x equal to 0, it is constant 0. So we have this function 2x equal to 0, only 4z square will be there. So it gives us z cube by 3, so 4 by 3, and dy will give 1, so it is 4 by 3. Right hand side we have to calculate the line integral, 4 line integrals, and then add them up, and it should be also 4 by 3. So for the first path we are going from in dy direction, so dl vector will be dy into j cap. So b dot dl in this case will be 2xz plus 3y square dy. And if we put the limit on y, because x equal to 0 and z equal to 0, here only variation is in y direction, so 3y square dy, and limit is 0 to 1, so it is 1. Similarly for path 2, dl vector is path 2, dl vector is changing in z direction, so dl vector will be dz into k cap. So only k cap or z cap will give us the values, other terms will be 0. So b dot dl will be 4yz square dz, and if you put the limit 0 to 1, dz square, it is 4 by 3. Similarly for the third case, it is again in y direction, so b dot dl equal to this value into dy, and the limits, because limit here we will take dl vector as positive, we can take the dl vector as positive, but because limit is going from 1 to 0, so that's why it will be negative. Here we are going, y is going from 1 to 0, and other terms are x equal to 0, so only 3y square will be there. So 1 to 0, 3y square, it will give us 0 minus 1, that is minus 1, and fourth is going 1 to 0 again. So we do not take this as minus z, but we will take the limits from 1 to 0, 4yz square, and it gives us 0 also. So b dot dl, if you add these all 4 line integral, it is 1 plus 4 by 3 minus 1 plus 0, that is 4 by 3. So left hand side and right hand side are equal. So you have first calculated the surface integral here, or curl, and then it was 4 by 3, and here we have the bound 4 lines or boundaries, so 4 line integral you have added, and finally we get the left hand side and right hand side equal. So Stokes theorem is verified for this. So this was all about the fundamental theorem on gradient, divergence and curl. So thanks for watching this video.